This is the four-leg robot. This has a different name of the robot, but I think this robot is very useful. It can be applied to a lot of mobile robot in the future. Today we will look at the case of the robot from Switzerland, from China, from United States. There's a lot of robot. I'm gonna start about talking about what it is. There's been a lot of robot developed in the last decade, and this is to introduce some robot. This is the name StarlETH, which is a compliant quadrupedal robot that is designed to study fast, efficient, and versatile locomotion. The platform is useful and is fully actuated with high compliance series elastic actuation or actuators, making the robot torque controllable. At the same time, it is suited for highly dynamic maneuver. So the keys of this is to power the real-time control and the simulation environment. The work is with number of experiments, and we're talking about the introduction of it. Inspired by Locomotion in natural, research in electric robotics is currently undergoing substantial changes. In contrast to early walking machines, as we know, a wheel robot. This is a stiff and controlled kinematically more and more compliant system, and nowadays finding their ways into robotics. So this offering an entirely new field of research. Due to their mechanical softness in terms of back drivability, low system inertia, and those systems are perfectly suited to continuously interact with their environment. They can cope with ground contact, collisions, and are at the same time safe for hand-in-hand collaboration with human operators. So it's similar to the natural creature. This is the four legs, and this is compliant elements in muscles and tendons likely contribute to energetic efficiency, and spring can be exported in robotics to support nonlinear oscillations. So we implement some flexibilities into it. It will give you just the physical phenomena like the muscles and tendons. But it will give you some nonlinear oscillations. Transition from classic industrial robot to such novel platform is accompanied with paradigm shift from position control to torque control strategies. For example, with research done with DARPA Learning Locomotion Challenge, have shown that how far position control strategy can be pushed to precise kinematics trajectory planning and execution, but at the same time, it challenged the limitations of stiff position control, since the detailed knowledge not only about the internal state of the robot, but also about the environmental is required. So there is some limitation to cope. So the new torque control approach allows to modulate the system behavior in sophisticated and adaptive manner to combine the advantage of efficiencies and versatility in single device. So this robot was developed to push the state-of-the-art in the field of compliant quadrupeds. This paper or research also introduced some hardware prototype and reports on tests in several statics and dynamics experiments. So it starts from simulation and control environment in detail, and proper integrations of software and hardware can lead to extremely powerful of development. So let's look at the hardware. I will give you some descriptions of the hardware. It is the 4 identical legs that are arranged in X configurations with linear dimensions about 0.6 meter and total weight of 23 kilograms. The size is like a dark, medium dark. Enable legs has 3 degrees of freedoms. So the leg length is about 488.5 millimeters, and the segment length is about 200 meter, and it can have a payload about 25 kilograms, and max hip torque is about 24 Newton meter. Max knee torque is about 14 Newton meter, and we do have some maximum minimum of the hip angle rotation and the speed of the hip, the knee, and the motor power that used for the robot is about 200 watt. So one of each hip is used motor at same as the hip abductions or adductions, and hip flexions or extensions, and knee flexions or extensions. These are used and controlled by the actuator's motor. The robot design is based on early studies that we optimize it from a planar running leg. This leg was attended with abduction degree of freedom. The key data of mechanics as well as actuators are summarized. So we put emphasis on keeping the initiator of the moving segment minimal by concretation of actuator at the main body through the use of chains and cable pulley system. This is benefit to ensure fast swing leg motions and introductions impact loss to emitting ground contact. Okay, and when we want to look more in the material, this is the lightweight main body. It fabricated as a carbon fiber sandwich monocoque with aluminum front and back connectors. It contains well protected all electronics part that's cooled to active air circulations. The key elements of this will be the high compliance series elastic actuators that are implemented in all joint using linear compression spring in pre-compressed setup. This is at the hip joints. Spring decouple the motor. The motor is the Maxon's EC 4-pole 200 watt and 200 watt, and gearbox is harmonic drive with the 1/1000 reduction ratio from the joint. So this setup ensures robustness against impacts, allow for energy storage to improve the efficiencies, and provides full torque controllabilities. All joint angles, motor angles, and spring deflections are precisely measured in every joint. The high weight ball feed, as based on air-filled racket ball, are based on air-filled racket balls. Yes, and that is the feed, and provide the cushioning with minimal weight while having a high contact friction coefficient to detect change in contact force. We tightly integrate force sensors, resistance, which is FSR, that is proprioceptive sensors. It's just the sensors equipments with complete with the Exons MTI IMU that include accelerometers and gyroscope. So during the simulation task, this is the highly complex inherently unstable system. So with 12 actuator joints and 6 unactuated, which is a floating base, unactuated floating base. Degree of freedoms is an often unknown environment requiring a powerful and reliable control system. After several iterations through different configurations, it can be realized that some framework can be really useful. So some of those framework can use in Linux host PC and is quite useful for real-time simulations and control environments, which is based on SL, analytical global kinematics and dynamics. The framework also allowed immediate exchange of simulation actual robot, and as well as integrate into the iOS ROS. After seeing different configurations and this framework, the setup is based on a single utilized host PC, which is responsible for entire high-level control part. The software contains a real-time simulation and control environment, which use the multi-body dynamics engine for visualization of the robot and its environment, as well as for handling the internal masses between different servo and memory and signaling. And additional is will take care for data locking and also post-processing. Another core element is the servo motor, which is responsible for timing and control the coordinate of individual actuators. It contains all low-level regulators, which is positions like velocity and torque at Fignose filters, using either memories to access the simulations or the communication like CAN bus gateway to communicate between the actuator and allow user to be able to possible to run simulations and experiments with the same controller implement. So this is the advantage of the control development, since it's avoid the code re-implementations. So it's amplifier for debugging and testing, and ensure the certain safety for control is good and robust by using the simulations. In the ROS or ROS, servos provide interface to the robotics operation system, which can meet the high real-time constraint of SL, which is connections is open for a use of interface and sensors, and allowed a lot of package to communicate. In this setup is include IMU and the measurement system like Kinect sensors, and as well as several external device such as the control like joystick to set the positions and orientations of the robot. And the final things is a task decouple the controller, which is entirely from multi-body simulations, and this also provides the global kinematics and dynamics of the robot. And this is the analysis simulation tool, so it developed on a Pro NEU on a MATLAB framework, and we use a symbolic math toolbox in order to use the kinematics and relative kinematic tree and change it to global kinematics using Euler rotations, and to derive the system dynamics using projected Newton-Euler equations. From over to the speed and simplifications of the implement, this separation between the model and the controller and the simulation have been some benefits. The control engineer has a user interface and access to any kind of updated kinematics or dynamics parameters, and about the sensors, which is imperfect state estimates. So just like the IMU, they introduce some difference between simulation and real things, and the control allowed to test the robustness of control against some errors, noise, modeling errors, and some limitations of the plant, some instabilities. The state estimators which implement on the top of the robot, and the models fuse kinematics informations with IMU sensor signal. This is based on actin Kalman filters, which is well used and well known for estimating the parameters from several signals and noise. This is allowed to generate the ground elevations map by using contact feed. So in summarize, there is the lead limitation factors, that is between the data connections of the CAN bus system and the host PC and the motor controller. And to do this, we have a bit rate of 1 megabit per second limitations for a loop cycle time about 400 Hertz. And we have 4 channels, 1 channel per 1 leg. So in the results, the first thing for the experimental validations is to test the performance just as walking, running the robot to make it sure it has sufficient torque to enable them to do the task and complete various maneuvers. That is something that we have to do, is to make robot stand. This is the completely change position from the course positions to the standing positions. So when we look at this, we also put a payload on the robot, and we can put a payload of 25 kilograms on the robot, and the robot can stand up, and this way is considerable enough payload for the robot for our design. So in the theory, the peak torque at a knee of 40 Newton meters with a lever arm of 8.2 meter results in a maximum total lift force about 800 Newton, or a maximum standing up payload is about 50 kilograms. But however, this peak could only occur in highly dynamic maneuver, and were hence not experimentally validated for safety reasons. To be capable to perform dynamic maneuver, it is crucial the system can cope with impacts. In contrast to a stiff system, as we said, the pre-impact kinematics energy should not be entirely dissipated in collisions that harm the mechanical structure. Instead, the system should be able to dam out a certain amount of energy, or to store it as a potential energies in actual spin. To demonstrate both, we drop this robot from a height of 0.5 meters. The passive mechanism complies with actuators, as well as the high damping feed elements, compact the system from the impact at landing. This ensures that if all motor are blocked, none of the gearbox get damaged. None of the gearbox get damaged to high peak force. The high compliance spring lead to lag oscillations. Yeah, the high compliance spring lead to lag oscillations. Red dot line in the results shows some number of short rebounds. That is the results after putting the robot on the ground. So with a passive compliance, comparing with the active damping. So, what to say? Even if our motor is blocked, none of the gearbox get damaged. So this can be avoided to active damping using a virtual model control system with some exerts of the force and the main body, with some primary represents the main body position and orientations, the spring and damping constants. In combinations with additional gravity compensations, the force distributions onto different contact force, and those contact subsequently translate into joy torque using a Jacobian transpose mapping with the related Jacobian at contact point. So this summarize will talk about the fast, efficient, versatile locomotion's lightweight system is driven by high compliance series elastic actuators. Does make fully torque controllable robust against impact, hence perfectly suited for sophisticated dynamic maneuver. A framework based on SL combinations with an analytical global kinematics and dynamics implement serve a powerful real-time simulation control environment, and it give control engineer user failure to develop and test control algorithms for the robot. And this robot can be successfully tested in various experiments that demonstrate the high torque capabilities and implicant protections against impact collisions and full torque controllabilities. And the platform, the combination between the control and simulation environments perfectly suit for dynamics maneuver and sophisticated model-based torque control strategy. At the first step, successful walking experimental will conduct using present virtual model. Yes, that would be an interesting thing to develop.